So we are looking at a nonlinear spring, as we have said, and which f equals kx squared. I expanded in Taylor series. Take the first two terms. So this is x, this is, let's say, f. And kx squared would be a parabola like this. Let's say that this is our equilibrium point, x0. This is f0, f0. So I define a new coordinate again, as I have said. This is delta x. This is delta f. And the slope here is simply 2k x naught. And this is the equation that describes our system. This is unnecessary. So, for example, this is a nonlinear spring linearized about an operating point. Now we can add a mass to this spring.
Hocam, may I ask something?
Sure.
About the equilibrium point. So we just choose the initial points as the equilibrium point? Is it the case?
Well, no. Usually the system, a physical system has an equilibrium point in which the system operates usually. For example, as I gave you the example, it is the mass spring system in which the gravity force and the spring force are cancel each other so that it is in equilibrium. That is the example I was going to give now, actually. So let's say you have a spring plus mass system. The equilibrium is a property of the system. We don't select it arbitrarily, okay? It is in which the system is in equilibrium. For example, I will give you examples, okay? Again, let's say that you have a spring like this and a mass. But the spring is again, let's say the spring force is kx cubed, let's say, not squared, but cubed. Doesn't matter, I could have selected square as well. And this distance here is x. Okay. Now, there is the gravity here. If you sum up the forces on this mass, you have mg downward, kx cubed upward, right? So the equilibrium means mg minus kx cubed equals 0, right? It is a static equilibrium, which means that x equilibrium value of x is simply cube root of mg over k. So this is the value of the equilibrium. Do you understand? So the system, without any force, stands in equilibrium at this value of x0, and the spring force would be k times this. Sorry, well, spring force will simply be k times this cubed, x0 cubed, which will be mg actually, eventually. Doesn't matter. This is the equilibrium. But there are other possible equilibrium. For example, if you have a pendulum.
Hocam, We just choose this point because we know the conditions of it, right? Because we can choose any point in the non-linear graph and linearize it. Because we can.
Yes, yes, but it wouldn't make any sense. You have to linearize it about the equilibrium. Okay? For example, if you have a pendulum like this, the pendulum equation is, as you know, is theta double dot plus g over L sine theta equals 0 if there are no forces on it. Okay? The equilibrium of this is given by sine theta equals 0. So the pendulum has actually two equilibrium points, not just one, which is sine theta equals 0 gives theta equals 0 degrees or theta equals 180 degrees, okay? So this is the regular pendulum, downward, and this is the inverted pendulum. Strange as it might seem, this is an equilibrium point for the pendulum, okay? Inverted pendulum. It is an equilibrium, but it is an unstable equilibrium. Okay, but let's not get carried away. There are equilibrium points in all physical systems. There are points in which the system does not change if there are no extra inputs on it, okay? So these are the equilibrium points. In the equilibrium, basically the derivative terms are in the differential equation. You set the time derivatives to 0, okay? So the system reaches a steady state when the derivative terms are set to 0. So you set the S terms in the Laplace transforms to 0. We will come to that later on. Okay, so let's continue with our problem. This was a pendulum. No, not the pendulum, this one, spring mass system. So how do let me just copy, let's not draw it again. Anyway. So here, summation of forces, summation of forces is equal to mg is downward minus kx cubed is upwards is equal to ma, which is mx double dot. So it is mx double dot plus kx cubed is equal to mg is our equation, okay? This is a nonlinear equation. So we want to linearize about x0, where x0, as we know, is mg over k times to the power 1 over 3. Okay, what we do is we want to expand the nonlinear function. We say that, first of all, x0 we take small changes around the equilibrium. So these are, well, supposedly small changes, delta x. But when you have a differential equation, there is something nice. X0 is a constant, okay? This is a constant term. Its time derivative, since x0 is constant, is simply delta x dot. And x double dot would be delta x double dot. So in the nonlinear equations, we have this x0 term drops in your derivatives. Now you have the x cubed term in this equation. We will expand this in Taylor series. X cubed would be, what will we do? D by dx. So we can write this as x0 cubed plus 3 x0 squared delta x, right? So this is the equation. Let's put it into here. And x double, instead of x, we will use delta x now. So change variables, mx double dot plus k times x cubed, which is this x0 cubed plus.
Hocam?
Yes.
Sorry to interrupt, Hocam, but the d over dx of x cubed, shouldn't it be at x0?
Huh?
In
Why?
the previous step,
D by dx of x cubed.
it's the derivative at x0, or no?
Yes, at x0. Yes, thank you. I wrote it correctly, that's right. Equals mg, that is this equation. This is what we get. Now we have kx0 cubed here and mg there. But we know that kx naught cubed is equal to mg because this is the definition of equilibrium. Okay? So this term and this term cancels. So what we are left with is delta x double dot plus 3k x naught squared delta x equals 0. So this is the poor drawing. So this is the linearized differential equation. X naught. It is true for, well, small changes, but you know, it's kind of okay for many purposes. Well, at least In this course, we are going to use only linear equations. Now, we won't go into anything nonlinear because it's too hard, really. And plus, in controls, we are dealing with small deviations about equilibrium, so we don't really care about too much big changes, okay? So most of the times, the linear equations are good enough for our purposes, practically, okay? So we got a differential equation, as we see, that is linear. We can work with this differential equation, and the variables are changed. The small, the deviation variables are the variables in for our system. So this is linearization for a single variable, but you can also do linearization for a large function with two variables, let's say, variables. It is possible that you might have a function of, let's say, y is equal to f of u1 For example, you might have y like this. You might get something like a surface here. Okay. These are constant lines. This is a function of two variables, y of u1 and u2 is a possibility, or you might show this function by like this, if you like. This is also possible. In some cases, y, let's say, this is u1. Y versus u1 is shown with like different plots like this one. This is, let's say, u2 equals 1, u2 equals 5, 2 equals 10, etc. These things are shown in the same plot. They are kind of identical, but you might show it. This is the 3D representation. This is the 2D representation, and you might have multiple functions, functions of more than one variable. Here, what we do is linearization. For linearization, what we might do is you can write y approximately as about if you select a y0 point, again an equilibrium, y0 plus del f del u1 evaluated at, let's say, u1, u2. u1 not, u2 not, rather. 1 minus u1 not plus well, it's just that actually we don't have to write these. This is all that is. So we approximate it by something like this. And in this case, therefore, we write we selected to this side delta y is equal to Okay, so this is a linear relationship, for example. Well, we have examples of that. I will give you this example later on, but let's keep it here. Well, let me not give that example. I have the example of the hydraulic actuator that needs to be linearized later on, but let's keep it. Oops, sorry. Let's keep that example for the case where we study the hydraulic actuators. So, I'll briefly go to one more tool which we use, as we know. And you know this, but you know it from differential equations, and you probably thought you will not use it. But this course heavily depends on Laplace transforms, so you better remember it. And I will just go through it quickly because I assume you know the Laplace transforms and how to use them from differential equations. Basically, Laplace transform is a transform that converts a function of time, f of t, by a transform, a Laplace transform L, to a function of another variable, okay, f of s. And we show f of s is equal to the Laplace transform of f of t, and its technical definition is f of s equals 0 to infinity, supposedly, of f of t e to the minus st dt. It is a very important transform, which is very commonly used. And it has relationships to Fourier transform and Fourier analysis and complex variables and so on. But I'm not going to go into details of it. The most important Laplace transforms, I will just give you a very short table. This is what we will be using most of the time, so that you might remember it. You might need to remember these only. If you have e to the minus at is a function, its Laplace transform is 1 over s plus a. If you have a 1, its Laplace transform is 1 over s. If you have the time function, its Laplace transform is 1 over s squared. Sine function, sine omega t, is its Laplace transform is omega over s squared plus omega squared. And cosine omega t is s over plus omega squared. Let me write it here. You can just derive these, taking these integrals, okay? It's not that hard. Well, obviously, for a few ones, it's not that hard, but it becomes harder for more complex functions. Very important for us are these exponential decays. it is omega over Okay, you don't have to memorize these. If needed, these I'm going to give them to you. But it is, you know, it's good to know a few of these so that you don't really well, spend time on these. For example, the Laplace transform of 1 to 1 over s is kind of obvious, so you don't have to spend time. Okay. So it is a transformation that transforms a function to another domain. Actually, that domain is a complex domain, but we are not going to use that. We are going to basically use Laplace transform as a kind of a differentiator operator. And
Tarlalarda da böyle.
pardon?
Elekler şey.
Sesinizi kapatabilir misiniz lütfen? Okay. So the properties, very briefly, I will talk about these. First of all, if you take the first of all, the Laplace transform is linear, so that a constant times f of t gives you that same constant times f of s. Okay. As a matter of fact, a constant times f1 plus f2 is so let me write this a. If you take the Laplace transform of this, you get a f1 of s plus b f2 of s. So it is a linear operation, Laplace transform. Okay. The derivative of this is probably our most important thing for us. The Laplace transform of a derivative of a function, time derivative, is s times f of s minus f of 0 is the derivative. It is possible to derive it, but I'm not going to derive it. You can just look at textbooks and so on. It is not only this, but the Laplace transform of the second derivative, for example, time derivative, obviously, is s squared f of s minus s f of 0 minus f I don't know what's going on. Minus so these are the initial values of that function. You have to subtract them from the function. In general, the Laplace transform of d to the dn to the f over the n can be written as s to the n f of s. time derivatives. Well, for our purposes, usually, as I have said, we will be ignoring these initial condition terms most of the time and use the Laplace transform to transform the nth derivative to s to the n times s. And the integration so the Laplace transform of an integral of a function, let's say 0 to t of this is also a function, this is nice because it is derivation means multiplying by s. Integration means, in the Laplace domain, dividing by s. They are the opposite operations. And the Laplace transform allows us to solve differential equations by converting them to algebraic equations. We can solve the algebraic equation and then go back transform our equation and then get the solution, which is very, very simple way of solving differential equation. If your differential equation is a linear one, of course, we are limited to linear equations, by the way, then you can solve it by using Laplace transforms. And there is one more property which is kind of important, which is multiplication by e to the minus at. So if you have a function f of t multiplied by e to the minus at, if you do this and then take the Laplace transform of it, it is very simply f of s plus a. If that is, you take the function and replace it by a from it. You can see it from the sine and cosine functions, for example, here. Here in these examples, I have replaced s terms by s plus a here, as you see. S term by s plus a. If you multiply by e to the minus at. Okay, these are the very basic properties which will be useful for us. There are a few more, but we will see them as we go on. Now, the main thing we do for Laplace transform is we try to solve differential equations. We try to solve them by differential. You probably have seen this, but let me just give you an example, a simple example. Let's say that you have a differential equation like this one, x double dot plus 3x dot plus 2x equals f of t. That's the differential equation. We take Laplace transform of this. So if you do this, you are going to get the following. You have the second derivative terms, etc. capital is the Laplace transform minus s x of 0 minus x of 0 is the first term, plus 3 times s x of s minus x of 0. These are the initial conditions, plus 2x of s equals f of s. Okay.
Hocam, is the last one big one, Laplace one, or normal one?
2x of s.
Yes, hocam.
Yes, it is the Laplace. Laplace transforms are capital, and for example, this is small case, x of 0. X of 0 and x dot of 0s are small case. They are count functions. They are constants anyway. So we can write x collecting the terms. We can write it as follows. 2f of s minus no plus s. S squared plus 3s plus 2. Okay. So for example, here we will try to solve this given f of s or t, doesn't matter, given f of s, let's say, x of 0, x dot of 0, solve for x of s, and then x of t is going to be the inverse transform of x of s. Okay. That is how we solve the differential equation. Well, the inverse transform is again, and actually it is, the definition of it is a complex integral, but we never do that. We usually do the so-called the partial fraction expansion. Okay. In short, we use PFE for that. And from there, we solve for the unknowns. Let's try to, we have very little time, so I'll just give you an example, very short example. Let x of 0 equals x dot of 0 equals 0, okay? And f of s, sorry, f of t strange things happen. I say that it is a 1, it is a step function, so that f of s is simply 1 over s, okay? So x of s becomes 2 times s times s squared plus 3s plus 2. Or you can write this as 2 over s times s plus 1 plus don't have the solution, well, we don't have such a function in our, usually in the Laplace transform tables. So we can need to do the partial fraction expansion by, I don't know, for example, what did I say there? A over S plus B over S plus 1 plus C over S plus 2, so that I can find these out. Well, you have seen this in your differential equations course. You basically find ABCs by equating the coefficients, multiplying them, and so on. As a matter of fact, I'll just give you the result. It is 1 over S plus, since we don't have the time, I'll do it this way, minus 2 over S plus 1, so this is a plus 1 over S plus 2. Now, these are all invertible functions. We know the solutions to them. So the x of t is the inverse of this, inverse of x of s, which is 1 minus 2 to the minus e to the t plus e to the minus 2t, for example, which is valid for t greater than 0. Okay. It looks simple, but there are problems. First of all, how to obtain these ABCs, I will review them the next time. How to find these ABCs. Secondly, there are the problem cases of if the roots are repeated roots are a problem. If the roots of this equation are repeated, or if you have complex roots, that's also a problem. So we will have to look at these problems the next time. Yes. So if you don't have any questions, that's all for today.
Thank you, Jim.
Thank you so much, hocam.
Okay,
Thank you hocam. İyi günler.
Thank you, John.